The normal curve shows up everywhere: exam scores, heights, errors, and measurements. But here's the key: the normal curve is not about data, it's about how outcomes are formed, and that's where most people misunderstand it. So let's first understand what is the normal curve. The normal curve or bell curve describes situations where most values cluster around an average, and extreme values are rare. It's symmetric, smooth, and predictable. But data doesn't magically become normal. The real question is, why does this shape keep appearing in real life? The first reason is many small additive effects combine. Most real-world outcomes are not driven by one big factor, they are driven by many small independent effects. Take exam scores for example: preparation, sleep, stress, difficulty, memory, luck all add up. When many small effects combine, no single factor dominates and results naturally move toward an average. Reason 2 is positive and negative deviations balance out. In real life, deviations usually go both ways. Some days things go slightly better and some days slightly worse. Because these deviations are roughly balanced, the distribution becomes symmetric around the mean. The third reason is extremes are naturally rare. Extreme outcomes require many factors to align perfectly. That doesn't happen often, and this natural rarity of extremes creates the thin tails of the normal curve. This brings us to the central limit theorem. All these reasons point out to one deeper idea: aggregation. And the central limit theorem is simply the mathematical statement of this idea. It tells us that when outcomes are formed by many small independent effects, the process of averaging those outcomes naturally leads to a normal distribution. The central limit theorem does not say all data becomes normal. What it says is this: when you take averages of many independent observations, the distribution of those averages becomes normal even if the original data is not. This explains an important distinction. Some variables like human height appear approximately normal in their raw data form. Height is influenced by many small additive factors like genetics, nutrition, environment, so the raw data itself forms a bell curve. Other variables like income are very different. Individual incomes are highly skewed and never become normal, no matter how much data you collect. But if you take many random samples of income and look at the average income of each sample, those averages do form a normal curve. That's the central limit theorem in action. Because the normal curve appears so often, it becomes extremely useful in practice. It allows us to quantify uncertainty and variability, estimate probabilities around an average, build confidence intervals and hypothesis tests, model measurement error, support forecasting and risk assessment. Whenever outcomes are driven by many small effects, the normal curve becomes a powerful and practical approximation. So the normal curve isn't a coincidence. It emerges because many small effects combine, deviations balance out, extremes are rare, and aggregation creates order from randomness. Real data science is understanding why this works and having the judgment to know when it doesn't.